Okay, so let's continue with this asynchronous serial data communication. So before this, we have looked at the synchronous serial data communication where we have the SPI, serial peripheral interface, and I2C, integrated circuit. But now we have another one, which is the asynchronous serial communication. So we have learned that FPI and I2C are actually very useful or when we want to transfer the data between devices. So it allows an easy way of synchronizing the data because we only use the clock to synchronize the data, right? So one clock cycle will represent 1 bit of data. So it is easy for synchronization. But we have a disadvantage of synchronous serial communication, where of course the clock is good for synchronization, but in terms of cost, we will see that the clock line itself add to the cost of the design because we have extra line for the clock. Uh, and also the bandwidth needed for the clock is always twice the bandwidth needed for the data, right? What is mean by this is this. When we look again at the synchronous serial communication, we have the clock. And this, for example, if we read the data at the rising edge of the clock, so the data will be something like this. Right? So when we look at this, this is logic 1, this one is logic 0, this one is logic 1, this one is logic 0, 0. So the data is 1, 0, 1, 0, 0. And we look at the duration of the data and the clock. So this one is duration for 1 bit, which is 1 clock cycle. All right. And if you look at the data, the duration of the data for one bit is you can see that this one is always double of the clock, and this one you can see double also because the data will be including the low time of the clock and the high time of the clock. So the size of 1 bit for the data is always double of the clock. This means that the frequency of this one, the clock, must be double. Yeah, the f must be double of the data frequency, right? That's why we say that the bandwidth of the clock is always uh, higher or double compared to the data bandwidth. So if our data uh, is for example the bit rate, so for example 2 megabit per second for the data, so the clock frequency must be double as that, must be 4 megabyte megahertz, yeah, in order to transfer 2 megabit data per second. So we need the clock that is 2 times faster than the data. So this is not good actually because uh, you cannot go to very fast or you cannot go have very fast transmission, because the speed has a limitation, right? The clock speed has a limitation. So for example, if the clock speed is limit to 10 megahertz, means that the maximum speed, data speed, is only 5 megabit per second. You cannot go more than that. So that is the limitation of uh, of this synchronous serial data communication. So it always depend on the bandwidth of the clock, and the clock is always twice the bandwidth of the data. And also, for long distances, clock and data themselves could lose synchronization. Means that if you transfer, if your line is long enough, so it may get unsynchronized between the clock and the data, and this is dangerous, right? Because for example, this we lost the synchronization. So for example, if move a little bit later here, yeah, here. So instead of we have 1 just now we have 0 here and we have 1 here. So this is called uh, unsynchronized. And this can happen, yeah, because in our serial communication lines, it is at, or it's used different wire, different line. All right, so it can unsynchronized, yeah, if we have long wire, right? Because remember, the wire will introduce a capacitance, and this capacitance will delay the signal. So it's different between this wire and this wire. So yeah, over long distance, it may unsynchronize the data and the clock. So for that reason, there are other serial communication standard has been developed, that uh, do not require a clock signal to be sent with the data. Means that we don't want to use clock, only the data at the communication line. So this is called the asynchronous serial communication. But the problem again is that how we recognize or how we differentiate between uh, the bit, yeah, whether it is 0 or 1, right? So for example, the problem with asynchronous serial communication is that if we have clock for synchronous synchronous serial communication, we can easily differentiate between this and this. So this is easily recognized as 0, 1, 0. This is 1, 1 bit, 1 bit logic 1, not 2 bit logic 1. But if we don't have clock, how do we know that this is only 1 bit 0 and this is only 1 bit 1? It can be 0, 0. It can be 0, 0, 0. And here also it can be 1, 1, or can be 1, 1, or can be 1, 1, 1, 1, or anything, right? So how do we know that? So we need another way to communicate between the sender and the receiver. So that approach is to use the duration of each bit, right? So for example, if we agree between the sender and the receiver that each bit, the size of each bit is 1 microsecond. So if this is the uh, sender, this is the receiver. So if the receiver receive the data that is 1 microsecond in duration, it will know exactly that this is 1 bit 0. And if you have another one here for 1 microsecond, so it will know exactly also this is logic 1 and this is only 1 bit, right? But if it receive something like this, 2 microsecond, so it know also now, because this is 2 microsecond and the duration for 1 bit for or each bit is only 1 microsecond, so it will know already that this is actually logic 1 1 1 1. So that is how the communication is done by uh, asynchronous serial communication. So remember, for the synchronous serial communication, we use clock to differentiate each bit, between the bit. And for the asynchronous serial communication, we use the duration of the data, the bit. So now again, uh, how to tell the receiver that the data is start and the data is end. So first, normally in asynchronous serial communication, or the one that we use is the UART, Universal Asynchronous Receiver Transmitter. The idle line, or the time that there is no communication, the logic at the data line is 1. So to start the communication, normally we pull down the data line to 0, and this one we call a start bit. And this is again, the duration is agree between the sender and the receiver here, right? The duration is 1 bit, yeah? The start bit and the duration is 1 bit, and after that is the data, right? It can be 8 bit, can be 7 bit, depend. So normally the data is 8 bit, and after that we have another bit, we call it stop bit, and normally the stop bit is logic high, and the duration is again 1 bit. And sometimes we have extra bit for error checking. We call it parity bit, right? So it depends whether we want to use or not. But I will explain later what is this parity bit. And before you have the stop bit, and the line will go back to 1 after that. So this is optional parity bit. So parity bit is the error checking, method. Before this, when we look at SPI and I2C, uh, when we send the data between the transmitter and receiver, when we send the data, for example, the 8-bit data, 8-bit data, so there is no way that the receiver know whether the data that it received is correct or not, because there is no error checking features here in the protocol, right? So for example, the data is the 8-bit, right? So the data is A1, okay? A1 in binary is 1010 0001. What if, because remember you send this as an electrical signal, so it will induce noise, right? So you will have losses here. So sometimes it will affect the data that you send. For example, what if this one change to 0 at the receiver end? So there is no way that the receiver here will know that it received the wrong data, right? Because there is no error checking, so it will just receive. So that is the problem. One of the problem is the communication also, whether it is parallel or serial communication. So the parity bit is used for error checking purpose. So how it works? So when we look at the parity bit or parity or error checking, so you will learn this in detail if you are in or if you learn the communication system, right? It is one of the error checking method for data communication, right? So there are two parity, can be odd parity or even parity. So for the communication, the sender and the receiver need to agree whether want to use the odd or even parity error checking. If we want to use, yeah. So this is optional, remember. So if we don't want to use, so we don't have this. But if we want to use, we have this extra. So we can set in the programming whether we want to use or not. So for example, we want to use, and if we want to use, we need to agree uh, whether we want to use which one, odd or even. So for example, we use even parity. So this one also need to use even parity. So how the parity work? The parity work is by insert uh, the bit value here, whether 0 or 1. If we agree to use even parity, so the total number of 1 of logic 1 here uh, for the data including the parity bit must be end up with an even number. So if we agree to use odd number, so the number of 1 and between the data and the parity bit must be odd number. So for example, in if we want to send the data in the serial line using the UART protocol, so again our data is A1, right? So A is 10100001, and for serial communication, for asynchronous, for UART, we will send the LSB first, all right, followed by this bit until the last one is MSB. So in the line, actually, you will have, you will see if you use oscilloscope to see the data in your serial line using the UART protocol. So what you can see is actually 1, yeah, and then 0 0 0 0 1 0 1. So this is your LSB, this is your MSB. So meaning that the at the receiver end, the receiver will receive the LSB first, and the last one is MSB. So that is how we transfer the data in or using the UART. Now, again, we want to use even parity in our case. So what we do is that this is done automatically by the microcontroller. So it will check number 1 in this data. So for example, this is 1, 2, 3. So the total of number 1 is 3, right? 1, 2, 3. And this is an odd number. And because we use even parity, we need to add another 1 for the parity bit, such that the total number of logic 1 for the data that we send is equal to 4, which is an even number. Like this. So in this case, the parity bit is set to 1. So let's say, for example, we send this value to the receiver through the line here. And remember, this data is A1. And let's, for example, same thing happen here, right? We have noise, and one of the bit here changed to 0 here. So now at the receiver end, it will count the value of 1 that it received. So here it received 1, 2, 3. Oh, number 1 that we receive at the receiver end is 3, which is odd number. Which is odd number. And if it is odd number, we already know that we use even parity. If we use parity and we receive odd here, means that something wrong must happen somewhere. So means that we must receive a wrong data. So the receiver can request to resend the data from the transmitter. All right. So that is how the error checking is done. But again, there is a limitation. What if before this, what if 2-bit, yeah, what if 2-bit, for example, this one go to 1, this one go to 0, right? Now this is wrong data also, and the receiver end will receive the correct one. We check, oh, this is even number, and yes, this is okay. The receiver said this is okay, right? So for that, we cannot differentiate. So that is the disadvantage. Yeah. For example, if more than 1 bit is corrupted, but at least we reduce the error by using the parity. But it is not perfect. Yeah, it can have this situation like this, where both this one change to 1 and this one change to 0, and we end up receive the even number at the receiving end, and this is looks like nothing happened, right? But it's actually the error here. So that is the drawback. And of course, the good thing is that we reduce the error, and the chances that more than 1 bit to be corrupted is actually very low, right? We learned already in digital design that digital signal is actually very less affected by noise. Yeah, remember in digital design. So this is actually the chances to have more than one bit to be corrupted is very small, but actually it happened. So back to this. This is the same thing that I have explained just now. This is how the data looks like in the UART protocol. We have idle state here, logic 1, and we have start bit, logic 0. And the first data here, which is the LSB. And we have the last data here, which is the MSB. And we have extra parity bit could be inserted here, could be, yeah, this is optional. And we have the stop bit, and stop bit is normally logic 1. And we have the idle state, logic 0. And just after that, earliest possible new start bit. So you can have a new data already. So it's straight away, you can have the new data. And this is how we use in the Mbed microcontroller. This is the API. And let's look at the Mbed microcontroller. This is the serial port or serial asynchronous data or UART. We have three. One is P9, P10, where P9 is the TX, TX is the transmitter, and RSX is the receiver. So in this case, if we want to communicate between the two devices. The first one is, of course, the microcontroller. The second one can be microcontroller or any other devices. Can be the LCD, can be the sensor. So you need two wire. One is the TX, and another one is for RX to transmit and to receive. Right? And the communication is now 1-to-1. Okay, the communication is 1-to-1. So if you have another one, you need to use other port. So this is the limitation of the UART also, right? So for example, the Mbed microcontroller, you can connect up to three devices. 1, 2, 3. So the other one is P13 and P14. This one is P38 and P27. So again, we use the same setup, but now we use the UART communication instead of the SPI and I2C previously. We want to do the same thing where we press here and the output is here. We send the switch condition through this line and look at the output here. And also when we press, here is the output. And this is how we do in this programming. So this is the name, the object name, P9, P10. So we use this P9 and P10. P9 is for transmitter and P10 is for receiver for the master. And also for the second one, should be different, right? This is for the first test. Right? For the second one, this must be like this. So I will. This is a little bit wrong. RX here should be to P9. Yeah. So this is yeah. This RX should be connected to P9, and this one is like this. Yes, because this is the transmitter for this and this is the receiver for this. Yeah. So I will update the notes and share with you. So this is the object name and of again the LED and the switches here, and we have the variable switch word the same, and we have another variable to receive the data from other microcontroller. And first thing we need to do is in asynchronous serial communication is this, where we need to define the transmission rate. And the transmission rate for asynchronous serial communication is in the unit bit per second, right? Or we call it baud rate, baud rate. So for example, if we have 9600 here, means that that transmission rate is actually, yeah, if we have transmission rate, or we call it baud rate 9600, means that this is actually 9600 bit per second, means that the duration of one bit, and if our this is the line and this is start bit, so the duration of this is 1 over 9600, which is actually when we use the calculator, 104 actually, 104 if I'm not mistaken, 104 microsecond, 1 over 9600. So we have yes, 104 micro, 104 microsecond, yeah, approximately 104 microsecond, right? So means that if we have, if we receive this the data like this, and for example the duration is 208 microsecond, this means this is 11, yeah. And if this is 104 microsecond, means that this is only one bit zero. That is mean by this baud rate. So default format is 8-bit, no parity. It means that in this case we're not using the parity. And this is the we read the switch again, same thing from the previous one, so I will not explain here. Now how to write to to the the line, transmission line. To write is easy. We use the function put, put c, the data that we want to transmit, and this is go, it will transmit to the to the uh, transmission line. All right, to the line here, tx to the, yeah. And this is to transmit. So to receive, yeah, because this microcontroller can receive also from here. So to receive, we can check whether there is data to be received or not. So this is how to check. We can have our object readable equal to 1, means that if there is data and we can read. So to read is very easy, and again we will read to a variable. So this is a variable that we have declared previously. So to read is get c, yeah, use function get c, and we can read. And again we can test the variable that we have, that we read in. So we can test if equal to 1, means that LED, red LED will turn on. If equal to 2, green LED will turn on. If both are pressed, means that equal to 3, both LED will be turned on. And that is how we use the UART. So you can see that the setting here, we can have three method of communication. First is by using the SPI. The second one is by using the I2C, and uh, the last one is by using the UART, or asynchronous serial communication. So we can use either one, depend on our application, and also depend on what kind of peripheral that we want to use also. So for example, if our app peripheral here, we want to connect with the LCD. So most of the LCD nowadays use the I2C serial communication protocol. So we need to use the I2C serial communication protocol. But if we want to communicate with other microcontroller, then we have any option. We can use any one that we want to use. But if we use the sensor, we want to read from the sensor. So the sensor can be anything. Most of the sensor nowadays, the digital sensor, right? So use the I2C communication protocol and also SPI communication protocol, right? Most of them use that. Uh, so for UART, there are some devices that use UART. For example, the computer, we want to communicate with the computer. Normally, we use the UART, right? The serial port. Okay. So in your project, you might want to use the digital sensor. For example, some of uh, your project, yeah, you propose to use the digital sensor. So you need to check in the datasheet uh, what is the communication protocol that that sensor use, yeah. Because if you have the embed library to read that sensor, then it should be okay, because the communication protocol is done by the embed library. But for example, uh, there is no embed library for your sensor, then you need to, yeah, you need to understand exactly how the data is the communication is done. Uh, so if it is used I2C, then you need to use the I2C protocol in order to communicate with your sensor, and also the LCD. Yeah, so you can use in your project as well, right? And we have learned already the drawback of the each of the communication protocols. So they use, whether we want to use uh, which one is depend on the peripheral that we use, and also depend on our application that we want to develop, right? So that will end the uh, this chapter 5, and next week we will start with chapter 6. Done. Thank you, and see you next week.